As part of the present administration's efforts to curtail the spread of coronavirus COVID-19 ravaging the country and the world at large, Edo State Ministry of Education, in collaboration with Edo Broadcasting Service (EBS) and Academic Staff Union of Secondary Schools (Asuss), is organizing a television program for students in senior secondary schools, particularly those writing the West African Senior School Certificate Examination (WASE), the National Examination Council (NECO), and National Business and Technical Examination Board (NAPTEB) for the year 2020 in the months of May, June, and July. The program will be held on EBS television channel every day from 12 noon to 1 p.m. beginning from Monday, April 6, 2020. The subjects selected for these programs are Mondays Mathematics, Tuesdays English Language, Wednesdays Physics, Thursdays Biology, Fridays Geography, Saturdays Civic Education and Economics, and Sunday Chemistry. Parents and guardians are therefore advised to draw the attention of their children or wards to this opportunity during the stay-at-home period.
Good evening, viewers. Famous Ethereus are my names. I'm your chemistry instructor for today. Today we are going to be looking at another aspect of chemistry, which is the practical aspect. The practical aspect of chemistry is of two types: the volumetric and the quantitative analysis and the qualitative analysis. The quantitative analysis is all about volumetry analysis. Volumetry analysis is a procedure that is mainly used in determining the concentration of a solution by titration. Today, we are going to be looking at the volumetry aspects of the practical chemistry. Now, we have apparatus that is mainly used in carrying out this volumetry analysis, known as titration exercise. The apparatus are so simple. We have the pipette, we have the burette, we have the funnel, we have the conical flask, they also have the beaker, and our restor stand. Likewise, our indicator, meter orange and litmus paper. In the setup, you are expected to be given at least 6 conical flasks to work with. 5 of the conical flasks is expected to be used in carrying out the titration exercise without alternating them or using any of the conical flasks. You have to use it just once. One of the conical flasks will be served as your control, as a guide to know your exact end points. In carrying out your titration exercise, a setup of this format is carried out, whereby the acid which should be given to you in a beaker as unknown substance, and you're going to use your indicator to determine which of the unknown substance is acid or base. The acid is expected to be turned into the burette and not the base, called the alkali, while the base is expected to be pipette. Most time you are given a pipette of a measuring size 20 cm3 or 25 cm3. But it is advisable you use 25 cm3, which is the most common pipette that is used by most schools or students. You are going to pipette at 25 cm3 of the unknown substance that you are going to determine into a conical flask. While doing that, you are expected not to blow the last drop of the liquid substance in your pipette into the conical flask, because in your mouth there is a liquid substance called saliva, which is also an alkaline. In the process of blowing the last drop, you might definitely alter the concentration of the unknown solution that you have in your conical flask. After pipetting, you are going to add indicator as instructed in your question. You are going to add at least 2 drops or 3 drops of indicator to the major unknown solution that you already have in your conical flask. Don't also forget that while pipetting, your pipette have a line known as the meniscus. That is the mark for 25 cm cube. If you are pipetting above the meniscus, that means you have more than 25 cm cube of the contents. For you to be on the safer side, you have to watch out for the line, which is the meniscus line. You have to watch out for the meniscus. When you pipette above the meniscus, you use your tongue to release some substance. Open your tongue gradually for the substance you already have in the pipette to gradually drop to the level of the meniscus, which will now be your exact 25 cm cube that you are going to have in your conical flask. When you are done with that, you have to pour in your acid that you already determined using your litmus paper. Don't forget that if you are given a blue litmus paper, know that blue litmus paper in acid medium will definitely turn red. If you are given a red litmus paper in basic medium will definitely turn blue. That will help you to determine which of your known substance that is given to you that will be turned into the burette for your titration process. After turning your acid into the burette, before running your titration, before opening your tap, you are expected to remove the funnel from the burette. And also, you are also expected to allow some liquid substance you have in the burette, the solution you have in the burette, little of it to be run off to avoid air bubble, because to avoid obstruction in your reading. Because in the process of turning your acid to the burette, air goes along with it. So you cannot run the titration in that manner. Rather, you have to remove some of the quantity you have so that the air bubble will be removed. Having done that, you take your readings. Don't forget that your burette is calibrated from 0 to 50 cm cube. Each calibration is of 0.1 cm cube. Whatever you have after you have removed some excesses, you take your reading, which will be called initial reading, that you are going to be recorded in your table. Most time you can use your 0 as your initial. You can use your 1, 2, 3. All depends on what you have in your burette after you must have removed some of the quantity. Having done that, some precautions are put in place while doing this to avoid errors. Make sure your burette is in a straight order. That means your burette must be straight, not slant. And your resting stand with clamp that is carrying your burette must be placed in a table that will not be too difficult for you to take readings. You are not expected to climb any object like your stool or chair while taking reading. It's very, very bad. So in that case, you have to take your resting stand to the level whereby you can take your reading without stress. And also, don't forget that whenever you are pouring acid with the help of the funnel, you have to pour it gradually so that some of the acid will not split and go will not split and run alongside the burette. By doing that, that can also affect your readings. That can also affect your readings. Okay. Okay, whenever you are pouring in your acid with the help of your funnel, you should pour that acid into your funnel to burette gradually to avoid spilling, so that some of the content of the acid will not have access to the solution you already have in your conical flask. You are also expected to have a white tiles. In the absence of a white tiles, your white paper can serve that use that you are going to place under your resistor stand, the base of your resistor stand, for easy detection of color change. That is for easy detection of endpoints. That's the reason why you must have a white tiles or your white paper at the base of your resistor stand while carrying out this titration process. When you are done with that, you are expected to run this exercise 5 good times for accurate readings. You are expected to carry out this exercise 5 good times. That is why you are going to be given 5 conical flasks for each exercise. Having carried out all this, don't forget to take your readings. In taking your readings, you are going to have a table, just like what I have here. In your table, don't forget to indicate the volume of pipette that you are using, because it is stated there that you can either use 20 cm cube pipette or 25 cm cube pipette. So you must state the volume of pipette that you use in carrying out the titration. And don't also forget the decimal place. The decimal place you have for the volume of pipette will also correspond to what you are going to be having in your table. Then your table must carry this heavy, tighter value. Your burette reading that will measure in centimeter cube. Your rough, your first tighter value, your second tighter value, your third tighter value. You can take it up to 5th tighter value. All depends on what you want to do. Like I've said before now, that when you pour in your acid to your burette, after removing air bubble, you must take reading, which can stand as your initial reading. Your initial reading can be 0, it can be 1, it can be 2, it can be 1 point, all depends on what you have in your burette. Now, take a case study of what I have on the board. This stands as my initial reading, which is 0. I'm taking 0.00 because I'm using 2 decimal places. I'll be corresponding with what I have with the volume of pipette. If this stands as my initial, that means I'm going to run a titration, allowing some of the acid to pour into the content I have in the conical flask that contain the metal orange, which is the indicator. At the end of the exercise, when I've observed color change, which is my end point, then I will stop the titration process and take my reading, which is the final reading. If my final reading is 22.10, what I need to do is to subtract the initial from the final to get the actual volume of acid used for that titration process. If this stands as my rough, because I want to be fast in my exercise, so I have to run a rough as that will give me a clue or a guide on where the endpoint lies. Then after the rough, I can carry out another titration with another conical flask. If I'm taking my reading, because this time around I'm going to top my burette, because I've already used 22.10 cm cube of the acid I have in the burette. This time around I'm going to top it for me to have my initial to be 3.0. It does not necessarily mean you must always stop. Your final reading for the first exercise can serve as your initial reading for the second exercise. But for simplicity's sake, because I'm already used to lower value, let's say 0.0 or 1.0, I can decide to top, I can decide not to top the acid in the burette. Now, in this case, I'm talking the acid in the burette. So my initial reading will come 3.0. If I also carry out the same exercise, I will discover that my reading, final reading become 25.5. Subtracting 3.0 from 25.5 will give me 22.5. The same exercise is carried for the second reading, third reading, fourth reading, and so on and so forth. Now, in this table, there are certain things you must put into consideration. Very, very important for you to earn a maximum point. Because your table carries more of the highest points as long as volumetric analysis is concerned. Now, there are some things we are going to look at, some practical instruction that we are going to look at in carrying out our titration exercise. As a student, it is advisable not to even go to the hall with a pencil because you might be tempted to use it. And the instruction is that you must not write any part of your question with a pencil. Either you are using it to rule or writing. After writing, you want to clean and write with biro. As long as a trace of pencil in your work, marks, you are going to lose some marks, at least 2 marks. You are going to lose it from whatever you earn from the table because you decide to write with a pencil. Writing the table without a unit. If you see what I did here, for me not to be writing units along the final and initial reading, I decided to put my reading, my unit here, CMQ. This CMQ will definitely affect whatever I have here because I already stated it. So no need of writing them again because I already have it at the top. So writing your values without a unit or using a wrong unit will also lead to loss of marks. Then consistently reading burette to the nearest whole number. Like what we have here, I've already taken my final reading, and my final reading here is 22.1. In mathematics, we are told that any value that is up to 5 can be rounded up to 1 and add to the next, and any value that is less than 5 can be rounded down. Because this one is 22.1, if I decide to say, okay, because it's 22.1, let me make it a whole number and write just 22. That means I'm taking the reading to a whole number, which is wrong. And I'm going to lose marks for doing that. Inconsistently reading burette to the nearest whole number of 1 decimal place. That means if I decide to have 22.1 here, which is 2 decimal place, coming down here, and I have 1, then here 2, here 1, as in alternative then. Assuming that does not mean, provided my volume of acid is the same, is wrong. Whatever you have on the table must be uniform in terms of decimal place. Putting down tighter value without showing how they arrive, either at the initial or at the final burette reading. Most times, students who always use 0.0 as their initial, because 0 is just a simple digit, then they will assume the initial reading and place it in their heart without putting it down and go straight to the volume of acid used. Since if you subtract 0 from 22.1 will give you 22.10, so students will assume that doesn't mean since it's the same, no need of putting the initial value. You go straight and write down the volume of acid used. By doing that, you will be scored, but you are going to lose some marks for not putting down or showing the initial and final burette reading. Deliberate obstruction of tighter value to agree with the teacher's tighter value. What does this one mean is that most at times when you are carrying out your practicals, your teacher is also expected to carry out the same practical with you on a separate classroom. And they are going to use your teacher value readings to assess what you have, because the analysis was carried out with the same solution prepared by your teacher. Now you already have a clue that your teacher value is 22.5. And already what you have in your reading is 22 or 23.1. Because if you subtract the initial from the final, it might not agree with your teacher's own. As a result of that, you decide to carry out altering of figures to agree with your teacher's own. By cancellation, by changing figures that will be easily pronounced, you are going to lose marks. If that color is what you use in averaging and is earning you a marks. But if it's not earning you a marks, there will not be any penalty for that. That means you are safe. So it is better when you have series of titration that you have carried out, the one that you have ordered, do not use it to average, because it might end you to loss of marks. For cancellation of table, if you cancel your table and rewrite another to agree with your teacher's own, there will be a penalty for that, because your former table is different from your new table. If your former table has the same value with your new table, there will not be penalty. And as a result of that, you will be on the safer side. But if your table that you cancel and you write another one that agrees with your teacher's own, you are going to lose some marks. Now, having known this, we are going to look at averaging. Most time, it is better you average with 2 tighter values than averaging with 3, 4, 5, depending on what you have. In averaging, they what we call concordant values. Concordant values means range. The range of the value you are averaging. It must fall within the range of plus minus 0.2. The value you are averaging must fall within the range of plus minus 0.2 for you to be scored in your average. If this value you have and differ from 0.2, even though what you have is correct, you lose some marks that is attached or allocated to average. Now, to be on the safe side, it is better you don't take more of your tighter value in averaging. If your rough is closer to every other tighter value you have, rough can be used for averaging. But it's better you look at the values that are close, that falls within the range of 0.15 plus minus to average. So by doing that, averaging 2 values, for instance, we have the first and second tighter value that falls with 22.50, which is the first tighter value, 22.40, which was the second tighter value. Adding these 2 values together, divide by 2, will give me 22.45. I can decide to leave my 22.45 like this, or I will approximate it to 22.50. If I'm approximating this to 22.50 and this is what I'm going to use, On no account should I go back to this value again, because I will be penalized. I've already approximated, and that's the value I will use. Now, in the area whereby you decide to average with all the values you have, rough, first, second, third, what I have in my table, I have 4 different titrations: rough, first, second, and third. Now, I want to average all my volume of acid use. I will state them like this. Because the range has to do with subtracting the lower value from the higher value. What we have in the table of average is that we have 22.1 as the lower value, and we have 22.7 as the highest value. If you subtract 22.10 from 22.7, it's called that the difference is more than 0.2. Even though what you have is correct and your evaluation is correct, you will not be scored. No point will be attached to this because your value is not concordant. So for you to have a maximum point in average, the value you are using must be concordant. And for you to have a concordant value, the difference must not exceed plus minus 0.2. If it exceeds plus minus 0.2, the 2 marks that is allocated to the averaging will not be given to you. That is for the table. Now, for the whole of this table, in marking, whether you have up to 5 title value, we are going to pick your best 2 to assess you and score you, giving you your maximum points. And your best 2 will be from your average. If a student decides to use all the 4 title value for averaging, the student might not get points for the averaging, but in the table, the student can be scored. As long as the student value agreed with the teacher's own. In marking, we have maximum points to fall within the range of 0.15 plus minus. That can end you, let's say, 4 points. 0.2 plus minus, that can end you 3 points. Okay. For your averaging, like I've said, for you to have a maximum point for your averaging, your values must be concordant. Concordant says that the difference between the lowest value and the highest value should not exceed plus minus 0.2. If you now have a value for this and they want to score you on your table, for you to earn a maximum point, irrespective of the title values you have, you are picking only your best 2 to score or give you your maximum point. Now, in assessing your best values, we watch out for the range between your value and your teacher's own. If your teacher's value and your own, when compared, it falls within the range of 0.15, 4 points will be given to you, or maximum point will be given to you. If your value falls within the range of 0.2, when compared to your teacher's own, 3 points or lower point will be given to you when compared to the maximum. 0.3 will earn you lower mark. 0.4 will earn you just 1 mark. 0.5 different will earn you nothing in the table. It means that if you have a higher value in your table that exceeds your teacher's own, which is outside the range of 0.5, in your table you score 0. Then, if your average is not also concordant, you also score 0. But if your averaging is concordant, there's no way your table will not earn you some marks. Having known this, we are going to look at some likely examination questions. Considering question 1, you are provided with a solution A, which is sodium triaurocarbonate 4 containing 5.2 gram per dm cube. Solution B is a dilute hydrochloric acid of unknown molar concentration. Prepare 25 or 20 cm cube of the alkali, which is the base, in a conical flask or a suitable container. Add 2 drops of methyl orange indicator. Titrate with acid in the burette. From your result, you are asked to calculate 1. The molar concentration of the acid in mole per dm cube and the concentration of the acid in gram per dm cube. The concentration of acid in gram per dm cube is same thing as mass concentration. Now let's look at the solution. If you look at the equation of reaction, acid is reacting with a base. Hydrochloric acid is reacting with sodium triaurocarbonate 4. Sodium chloride, 2 mole of sodium chloride, 1 mole of carbon 4 oxide, and 1 mole of water are produced from the equation of reaction. If you look at the equation of reaction, the mole ratio of the acid to that of the base is 2:1, which is more important when it comes to calculation under this volumetric analysis. That means balancing of equation is very important. You must know how to balance equation in situation whereby equation is not given to you, for you to be able to determine your mole ratio of acid to base. Molar concentration equals to concentration in gram per dm cube over molar mass. It's a general formula that you must not forget. A formula that you are going to use in determining or solving problem as long titration is concerned. You must have to know this formula. It's very, very important. Looking at the molar mass of sodium triaurocarbonate 4 from the molecular formula, it will be given to you that sodium, the relative molecular mass of each constituent of either the acid or base will be given to you. Like sodium will be given to you as 0.3, carbon will be given to you as 12, oxygen will be given to you as 16, hydrogen will be given to you as 1, chlorine will be given to you as 35.5. Now if you calculate the molecular mass of sodium triaurocarbonate 4, because sodium has 2 atoms, which is 2 times 23, plus carbon 1 atom, which is 12, 1 times 12, plus oxygen, which is 16 times 3, 48. When you sum everything up, it will give you 106. Molecular mass of this salt or this base, 106. Is either you write it as 106 to be silent in the units, or you write it as 106 gram per mole. Please, if you don't know the units, just silent. Just write 106 and go away with this score, your maximum point. But writing 106 gram is a wrong unit. Even though your value is correct, you will not be scored. You will be penalized for this, for writing the wrong unit. So, to be on the safer side, when you don't know the unit, just silence. Write your figure and walk away. Now, looking at the molar concentration, which we are asked to look for, the molar concentration of the acid. The molar concentration of the base, we want to determine it. Since the molar mass of the base is 106, and the mass of the base that reacted from our question, we only have 5.2 gram per dm cube. That means 5.2 gram in 1000 centimeter cube, which is a standard value. Sometimes this value cannot be in dm cube. it might be in cm3, that is less than 1000 cm3. That means that is less than 1000. If I have 5.2 gram per 600 cm3, I cannot take that value as a standard. As a result of that, I need to standardize it. That means I have to look for the same concentration of that value in respect to 1 dm3, which is 1000 cm3. That means extra work will be needed. So in this case, molar concentration as given there, 5.2 gram divided by 106, we give you 0.05 mole per dm3. Now, in writing mole per dm3, you can write mole per dm3 in two ways. Either as mole per dm3 or mole per dm3. That is, you have a dot. Now, if I'm writing it in this format, I will put an hyphen. But writing mole per dm3 in this format, that is a wrong unit. Even though this value is correct, because I'm writing a wrong unit, I will be penalized. Take note of that. Suppose we have carried out this titration exercise and our average volume of acid used is 22.50. That means after we have carried out series of titration exercise, we have taken our average, and this is now our average. Let's assume that's our average in this question, 22.50. And we are asked to look for the concentration of the acid. Okay, using our general formula CAVA over CBVB, where CA is the concentration of acid, VA is the volume of acid, CB is the concentration of base, VB is the volume of base. Then the mole ratio of acid, which is Na over the mole ratio of the base. Now, write down this formula. Mass are located to the mole ratio, not the formula itself. If I have Na over Mb, no score. But if I have my mole ratio either 2 over 1 or 1 over 1, depending on the acid that is reacting, mole ratio of acid that is reacting to the mole ratio of the base. So my mass will lie on the mole ratio when this formula is being considered. Now, we want to determine the concentration of the acid. Ca times 22.50, which is the volume of the acid gotten from titration exercise. 0.05 has to do with the concentration of the calculated base. 25 cm3 is the volume of the base, and our mole ratio from our equation, acid is 2 and the base is 1. Writing out this expression in this format will earn you 1 mark. Ca, making Ca the subject to add 0.05 times 25 times 2 divided by 22.5 times 1. Making this Ca the subject will also earn you another 1 mark. Then your final value, which is concentration of the acid, most times we are going to leave it in 3 significant figures. If I have 0.11 and I assume that doesn't mean, and I write it as 0.1 mole per dm3, because it's not in 3 significant figure, it's a 3 significant figure. Even though this value is correct, I will lose the mark that is allocated to this point. So as a result of that, you have to be very careful when it comes to the concentration of acid from your formula. So you must always make it 3 significant figure, except otherwise. Then your units must be correct alongside. Now, what we look at the concentration of the acid in gram per dm3, which is the mass concentration of the acid. Using the same general formula, molar concentration equals to the concentration in gram per dm3, which is the mass concentration over the molar mass of either the acid or base, depending on what you are to determine. If you make the mass concentration the subject of formula, you are going to have molar concentration times the molar mass from our equation or from our formula. Molar mass of hydrochloric acid is 36.5. Either you write it as 36.5 gram per mole or you write it as 36.5. Not 36.5 gram. Gram is not a unit for molar mass. To determine the mass concentration of the acid used, concentration in gram per dm³ is equal to the molar mass, which is 0.11 times 36.5. That is coming from the molar mass of the acid. How do you get 36.5? Don't forget that we have one atom of hydrogen and one atom of chlorine. Hydrogen have a relative atomic mass of 1, chlorine have a relative atomic mass of 35.5. When you add them up, it will give you 36.5. If you multiply 0.11 by 36.5, it will give you 4.05 gram per dm³. That will now be the mass concentration of the acid. Let's also consider another question that might be useful in your exam. Question 2. 2 grams of sodium triazocarbonate 4 was dissolved in 25.0 cm³ of water. This was titrated against 25.50 cm³ of 0.05 mol per dm³. Hydrogen tetrahydrosulfate 6 acid at endpoints. From this figure, you are asked to calculate A, the molar concentration of the sodium triazocarbonate 4, B, the mass concentration of the sodium triazocarbonate 4 in gram per dm³, C, the mass of sodium triazocarbonate 4 left at the end of the reaction, D, if the reaction took 40 seconds to complete, what was the rate of reaction? Now, you have been given relative atomic mass of each constituent of either the acid or base. Sodium is 23, carbon is 12, oxygen is 16, hydrogen is 1. Now, let's look at the solution. Equation of reaction, what is reacting? If you look at the equation of reaction, what is reacting? Sodium triazocarbonate 4 reacting with hydrogen tetrahydrosulfate 6. And you're going to be having sodium triazocarbonate 4 sodium, okay, we're going to have sodium tetrahydrosulfate 4, that was 6, and carbon 4 oxide alongside with water. If you look at the expression, mole ratio of base to acid that reacted is 1:1. Using this expression to determine your molar concentration of the sodium triazocarbonate 4 that was used in the reaction, CABA over CBVB equals to mole ratio of acid to base is a vital formula that you must always use in solving problems. 0.051 is the molar concentration of the acid, which is given in the question. The volume of acid used is also given in the question, which is 25.50. This can also be gotten from your titration table if you are asked to carry out a titration exercise. 25 cm³ is the volume of the pipette used. In the situation whereby you are giving 20 cm³ pipette, you will use 20 cm³ place of 25. Times the concentration of the base, making CB the subject of formula, you are going to have 0.05 times 25.5 divided by 25, and that will give you 0.05 mol per dm³ of the base, which is sodium triazocarbonate 4. Now, the big part, you are asked to determine the mass concentration of the sodium triazocarbonate 4. To determine the mass concentration, using the general formula, molar concentration is equal to concentration in gram per dm³ over molar mass. You must know the molar mass of sodium triazocarbonate 4, which is 106. If you evaluate 2 atoms of sodium, which is 23 times 2, 1 atom of carbon, which is 12 times 1, 3 atoms of oxygen, which is 16 times 3, add them up, will give you 106. Either you write it as 106 or you write as 106 gram per mole. To determine the concentration in gram per DMQ, you are going to make the mass concentration of the solvent. Making the mass concentration of the solvent, you are going to times the concentration of the base times the molar mass of the base, which is 0.05 times 106. That gives you 5.3 gram per DMQ, which is the mass concentration of the base, which is question B part. Let's look at the question C. The mass of sodium triacylcarbonate 4 left at the end of the reaction. It means that not all the 2 grams of sodium triacylcarbonate 4 that was used, what actually was used in the titration exercise is what you have in your pipette. So to determine that, you are giving 2 grams of triacylcarbonate 4 that was dissolved in 25 cm3. Now from our calculation, we already have 5.3 grams per DMQ, which is the mass concentration of the base in 1000 cm3. 5.3 grams per DMQ means 5.3 grams in 1000 cm3, because 1 DMQ is equivalent to 1000 cm3. If 5.3 is present in 1000, what is now present in 25, which is the volume of the. Now, to get what is present in 25 cm3, we have to make the unknown x. Making x the subject, we are going to have 5.3 times 25 divided by 1000. That will give you 0.1325. Approximating this to 3 significant figures, you can have 0.133 gram in 25 cm3, not in DMQ. If you now write 0.133 gram per DMQ, that would be wrong. That would be wrong. And because of wrong units and wrong expression, whatever value you have here will not be correct. So as a result of that, it's either you write it in gram per 25 cm3, or you just silent and write 0.133 to be on the safer side. Now to calculate the mass of sodium triacylcarbonate 4 left, don't forget that you are giving 2 grams at the initial of sodium triacylcarbonate 4 that was dissolved in 25 cm3 of water. Subtracting this value that was used from 2, you are going to have 1.867 as the mass of sodium triacylcarbonate 4 that was left. Now, in the deep part, we are asked to calculate the rate of reaction in 40 seconds. Amount of sodium triacylcarbonate 4 that disappeared, that was reacted in 25 cm3, is 0.133 gram. If you divide that with the molar mass, that will give you the amount of substance that was used. Don't forget that amount of substance from our formula is reactive mass over molar mass. So the reactive mass is 0.133, which is the actual mass that reacted, not the 2. Divided with the molar mass of the base, you are going to have 0.00125 moles. Now to calculate the rate will be the mole over the time it took the mass to disappear, and the time is 40 seconds. Dividing 0.00125 by 40, you are going to have 0.0003125. This can be taken to standard form. 3.125 times 10 raised to power minus 5 mole per DMQ. With all this solution, you have put an answer to all the question that is given. Now, to recap again, in volumetric analysis, you just have to be very careful when it comes to table. The table carries your highest marks as long volumetric analysis is concerned. And in your table, you have to be very careful in your units. Make sure your unit is well stated. Make sure you don't alter your figures Make sure you don't cancel your table. Make sure your readings are consistent. Either you are maintaining 1 decimal place or you are maintaining 2 decimal place. And make sure your initial reading and your final reading are well stated. Generally, when you are using 0.00 as your initial reading. And in taking your average, be very careful. Make sure your values you are using are concordant. Like I've said, your concordant value must fall within the range of plus minus 0.2. That means how do you determine your good range? Just subtract the lowest value from your highest value. In our average here, we have the lowest value to be 22.4 and the highest value to be 22.5. If you subtract 22.4 from 22.5, you are going to have 0.1. That means 0.1 is within the range of plus minus 0.2. That will earn you your maximum points. Now, in averaging, it is better not to average using more tighter value. 2 or 3 is better to avoid lapses in your averaging. So 2 or 3 tighter value are best suitable for your averaging. And don't forget to put your unit correctly. If you don't know the unit, just be silent and write your figure and be on the safer side. Having known this, I will urge you to keep trying. Use this procedure to solve more problems of your own, and that will make you to understand this particular topic very well. Come your way next week or some other time. I urge you to be a good student. God bless you.